So last time we started to discuss a complex projective space, and I introduced a connection on the tautological line bundle, and then we computed the curvature 2 form, which is globally defined because it's a line bundle. Let me recall. So we computed the curvature 2 form, and in these the coordinates, these affine linear coordinates that we have always been using, it looked like this. That's this correction term, some digit bar, which let me call this index k here. All right, so what we okay, that's a globally defined 2 form, and it's a purely imaginary form. So I introduced the Subini-Studi form by taking this form, making it real, and normalizing it by 2 pi, because that's what we have in the definition of the Chern class. And what remained to be shown, for abstract reasons, we know that this is a real form. One can also compute it explicitly by introducing real coordinates here. What remained to be shown is that this is non-degenerate. Right, so it's a closed 2 form. If we know that it's non-degenerate, then we know it's a symplectic form. And that tells us then something about the cohomology of the space, as we have seen last time. Okay, so why is this non-degenerate? Let me complete the argument. So let's fix a real tangent vector. So let x be a tangent vector to CPN at some point L, where L stands for line, because the points of CPN are lines, and a non-zero vector, let's say. And so what we need to show that if I insert this vector into this 2 form, then the remaining 1 form is non-zero. Because non-degeneracy, we have to see two equivalent definitions. One refers to the nth wedge product, and the other one was concerned with the matrix consisting of the coefficients in this form if you expand it in coordinates. And the condition was that this matrix is invertible. And in terms of this matrix, it means that if I apply a vector to the matrix, a non-zero vector, then I have to get a non-zero vector. That's injectivity, but since it's a square matrix, that means it's inverted. Right? So that's what it means. It's a non-degeneracy. It's like the non-degeneracy for bilinear forms in general. Whenever you insert a non-zero vector, you have to show that the resulting linear form is non-zero. And in order to see that, I just have to find some vector which I can put in the second slot, which gives me a non-zero value. So I have to find this good vector. And in order to find, certainly x itself will not do the job because of zero symmetry. So I have to find something different. And in order to get that, I write this vector in complex coordinates. So write x in the form a complex vector y plus, and let me say first what y is, where y is a linear combination of the complex coordinate fields. So these are so there's a dual basis to this, consisting of ddz(j) and ddz(j) bar, and I only take linear combinations of the ddz(j's) here with some coefficients, c zeta j. And then there's of course also other, so then there's something for my vector x, there's something also, some coefficients of ddz(j) bar. And what are those? Well, since it's a real vector, this must be the complex conjugate of 1. Because reality means that if I conjugate the vector, I get the vector back. And so the other term must be the complex conjugate of this one. So that means here our y is simply given as the dzj bar dzj bar. So this is how a real vector looks, right? I've just split my real vector or extended it in this basis, which is not a real basis. That's not a real basis, but I want to write it in this basis because my form is given in this basis. That's why bar. Yes, I choose x to be real because this is a real form, and I want to show that it's non-degenerate as a real form. And this is why I only insert real vectors here. But I want to do the computation in complex coordinates. And the reason for that is because this is given in complex coordinates. Alternatively, I could express this in real coordinates and do everything in real coordinates, but it's simpler to do it that way. Okay, and also this way it's easy to find the vector which I have to plug in here to give me a non-zero result. Namely, we will now show that if I take the Fubini-Studi form, apply it to my real vector x, and now I have to insert another real vector here. And the real vector that I insert here is the vector I times y minus I times y. It's also a real vector because if you conjugate this one, you get the vector back. So the y gets y bar, the y bar gets y, and the I gets minus sign. So that's also a real vector, and this is the one I insert here. And now we show that this expression is non-zero. And if I had done this, then I'm finished with this discussion. Okay. All right. So let's see what we get. So let's compute this thing. So this is x comma iy minus iy bar. And now, okay, I insert what I have. So this x is given as y plus bar. Iy minus iy bar. And I'm now working with complex vectors, and I will use the C bilinear extension of omega Fubini-Studi when I apply it to the individual terms. Right? So this is always to be considered as a complex bilinear form here. For real vectors, this doesn't matter, but it's not anything like Hermitian, like for scalar products. It's just complex bilinear. Okay, so let's expand that thing. So if I have this term times this term, by complex bilinearity, I can drag the I in front, and then I have omega yy by skew symmetry. This is 0. And similarly, this term times this term gives me 0 too by skew symmetry. So only the mixed terms survive. So I have omega Fubini-Studi y comma, and then here I have to take y bar, and the minus I put in front. And the other term that survives is omega Fubini-Studi y bar, comma, and here I have to take I times y, and I put the I in front. And now by skew symmetry I can turn this around, and I get the same thing as here. I get a minus sign here, so the two things add up. So I have 2I omega Fubini-Studi y bar y. So that's what we have, and I have to show that this is non-zero. All right, so putting in this form, so there's this fact 2 pi I. This is the 2 and the I cancel with the 2 and the I here, and only the 1 on pi survives. So I get 1 on pi capital omega of y bar y. Also, this form is extended by complex bilinearity to complex vectors. And and now we can use this explicit form. And now you see also why it's convenient to use these vectors y and y bar only consisting of conjugated or unconjugated vector fields here, because here we have the corresponding dual one forms. And if I plug in two vectors into a two form, I have to plug in the vector here times the vector here and minus the other way around. But in this case, only one thing survives, namely I have to plug in the y bar into this term and the y into that term, otherwise it gets 0 anyway. If I insert the y here in this term, then I don't have anything which would give me a non-zero thing. So that makes it easy to do the computation now in these bases. Let's see what we find. So the first term, so I insert y bar comma y. So the y bar has to go in here and the y has to go in there. So if I insert the y bar in here, then this gives me as a coefficient zeta j bar, right? So that's sum over j. So that's sum over j. And then I have zeta j bar here. And then inserting the y in the second term gives me the zeta j. So that's what I get for the first part. And the second part, all right, let's see. Again, there's only one thing I have to consider, namely the y bar going in here and the y going in here. The other combination gives me 0. So let's see. So that gives me sum over j, zj times, and the coefficient of the y bar in here is the zeta j bar times sum over k, zk bar, and similarly, yeah, I get the zeta k. So that's what we find. Okay. All right, and so let's see. That is 1 on 5 times. So now maybe I also move this factor out of the bracket, so that simplifies the first term at least. So I move this factor outside. That's also a real factor, positive real factor, not important. And then I'm just left with this sum, and this is just if you use these coefficients zeta j to get a vector, complex vector, this is just a complex vector norm squared, right? So that's what I get from here, minus, and then the 1 on z squared. So it's here, and well, actually, maybe I move them both out. And then I have an additional 1 on z squared here times norm z squared minus, and then I can forget about this denominator here completely. And what do I have here? Well, that's also a Hermitian scalar product of the vector z with the vector zeta. So what we have is vector z and vector zeta. Interlinear. This Hermitian scalar product is interlinear. It's not here. That's what I get from this first term. And the second term gives me the same, but just conjugated. So if I multiply this with its conjugate, I get norms left vector squared. So that's what I found. Right? 1 on 5. So now let's see. The first term I leave unchanged. And for the second one, I now use the Cauchy-Schwarz inequality. So this is bounded from above by norm z squared times zeta squared, right? And because of this minus sign, I get greater than or equal. And so I have here z squared zeta squared. Good. And that looks fantastic, because the z squared zeta squared cancels this z squared zeta squared, and I'm just left with 1 times zeta squared. So what I find is 1 times this b factor times the zeta squared. And the zeta, these are the coefficients of my vector y. And this is not the zero vector, because if they were all 0, then y would be 0, and then x would also be 0. But x is not 0. So that means this complete thing is strictly positive. Yes. Yeah. And so we have shown that it's not 0, and that does the job. We have now seen that omega Fubini studi is a symplectic form on CPN. And as a consequence, we know that this omega and its powers represent non-trivial cohomology classes. And so this is now a compact symplectic manifold. And in this case, we have shown last time that the powers of this form represent non-trivial cohomology classes. In particular, omega Fubini studi itself is non-trivial. And omega Fubini studi, what is it? Well, that's this term. So the cohomology class of omega Fubini studi, which is this cohomology class, this is, well, that's the curvature of the tautological line bundle, right? So this is exactly the first Chern class of the tautological line bundle. And that's not 0 with cohomology class. It's non-trivial. So the tautological line bundle has a non-trivial Chern class, and therefore it cannot be trivial itself. Therefore, this tautological line bundle is not trivial. So that was one of the questions we had asked earlier when we defined the tautological line bundle. Have we just found a complicated way to talk about the trivial bundle? That's not the case. The tautological line bundle is not trivial. So that's one thing we see from here already. All right, and what I want now to show is, so we have found the cohomology of CPN, namely this Chern class of the tautological line bundle, its powers represent non-trivial cohomology classes. And my claim is now that this is all the cohomology, there's nothing else. So, opposition, the cohomology ring of CPN, cohomology. Okay, let me first. The kth cohomology of CPN looks like this. So whenever this Fubini studi form gives me a cohomology class, it's spanned by that. And when does this happen? This happens in even degrees. But of course only in even degrees until I pass the dimension of the manifold. The real dimension is 2n. So that would mean we get the span of the corresponding power of the Fubini studi class k on 2 for even k less than or equal to 2n. And those are the cases when these powers of the Fubini studi form give me a cohomology class. And in the other case, and in these degrees, this is really one-dimensional cohomology. There's nothing else in this cohomology. It's only one-dimensional spanned by this Fubini studi class or its power. And in the other degrees, there's nothing. So that's, in short, we have this. In this sense, the cohomology of the CPN is minimal as a compact symplectic manifold. There's only the cohomology that there has to be there. Proof. Well, since we have already found these cohomology classes, we only have to show that there's nothing else, so we only have to check the dimensions of the cohomology groups. Only need to show that the dimension of HK, which is usually called BK, Betti number, the dimension of the cohomology is called the Betti number, And we have to show that this is what we have here. So it's 1 for even k that goes to n and 0 else. Okay. And how do we do that? This I do by induction on the dimension n. And in order to proceed, I need a tool from cohomology theory, which is called the Meyer-Vietoris sequence, which I want to briefly recall. And the Meyer-Vietoris sequence is very useful in many cases when you want to compute cohomologies of specific spaces. So that's an aside. I will continue the proof, but here first, before I do that, I recall the Meyer-Vietoris sequence. And this is as follows. You have a manifold M. You want to compute its cohomology. And you have two open subsets, U and V in M, in such a way that they cover all of M. So the union gives you all of M. And now suppose we know the cohomology of U and V and its intersection too, then in principle we can compute the cohomology of M. That's basically what the Meyer-Vietoris sequence tells us. So let's see. In order to formulate it, I have to give certain inclusion maps names. So look at the following inclusion maps. Let me check my notes so that I don't use a different convention here. So we have first inclusion maps from the intersection of the two sets into both of them. So one into U, one into V. And then we have two more inclusion maps, namely the inclusions of U and V into M. I, U into M, and I2, V into M. So we have all these maps. And then the statement is, there exist homomorphisms . Let's check. Delta from hk of the intersection to hk plus 1 of M union, such that the following sequence is exact. Namely, so let's see, what maps do we have now? So let me write down maybe hk of M here. Now, I have an inclusion map from U into M induced by I. On cohomology, the induced maps go in the opposite direction, right? So then the induced map goes from M to U. So that would go to U, and I can do the same thing for V. And so I have I1 plus, I take negative of I2 star here. And from these two spaces, I have these inclusions here, so I can go back in the opposite direction, which gets me to hk of the intersection, which is induced by J1 and J2. And now we have this additional so-called co-boundary map, which goes to hk plus 1 of M. And similarly here, so this comes from hk minus 1 of the intersection. And then the thing repeats itself. Of course, it doesn't repeat itself infinitely many times. Here you go back all the way until you end up with k equals 0. And here you go up all the way until you hit the dimension of the manifold. Beyond that, there is no cohomology anymore. And this is the Mayer-Vietoris sequence, such that the Mayer-Vietoris sequence this one is exact. So that's the statement about the Mayer-Vietoris sequence, and that's what we will be using now. So this person Vietoris is an interesting personality. Leopold Vietoris was an Austrian mathematician, and he died at the age of 110. For some time he was the oldest Austrian citizen. Okay, and so this is the Mayer-Vietoris sequence, and now we want to apply this here in the induction step. So let's do the induction. So we want to show this statement on the Betti numbers by induction on n. Let's start with the induction beginning here. So this is n equals 0. In this case, well, what is CP0? CP0, that's the set of all lines in C0 plus 1, so in C. All one-dimensional subspaces of C. C itself is one-dimensional, so there's just C itself. So it consists of just one point, right? So that's a simple manifold. And we know its cohomology. The point has cohomology in degree 0, one-dimensional, and no other cohomology. And this is in accordance with the statement for n equals 0. And that's it. So now we have to do the induction step. That's the interesting part. So suppose we know the statement for Cpn, and now we want to use it for Cpn plus 1. And in order to do that, I want to apply the Mayer-Vietoris sequence. So I have to come up with these sets U and V. So how do I define these sets U and V? And for that, we recall that we have this embedding of Cn into Cpn given by our affine coordinates. Namely, the coordinate tuple z is being mapped to the line spanned by 1 comma z. I use the coordinates where the 1 stands in the first slot. Doesn't really matter. So that's this embedding. That's the coordinates that we have been using all the time. And my u, as u, I can now define the set of all those that correspond to all those points z which have, say, norm at most 2 or something. Let's say 2. So that would be the set of all lines of this form such that the norm of z is strictly less than 2. Strictly less because I want to have an open set. So that's my u. And what's my v? Well, v should be large enough to give me, together with u, give me the whole space. So I certainly have to take all those lines where z is in norm, let's say, larger than 1, for instance. But I also have to catch all those lines that are not caught by this map, so which are outside the scope. Which are those lines? Those are the lines that are spanned by vectors where the first slot is a 0 vector. Because when the first slot is non-zero, you can rescale this vector, or without changing the line, and you get a 1 here. But if it's 0, then you can't do that. So we have to also include all lines where you have a 0 slot in here. And then, what kind of a space is that? Well, this is all the lines which lie in the orthogonal complement of the first spanning vector. So that's really all lines in an n-dimensional. Actually, here it is. I want to do this, let's say, for because I want to pass to Cn plus 1. So here these are lines in Cn plus 2, right? So these are lines in Cn plus 2. And if I put the first slot to 0, then I'm left with the lines in the orthogonal complement of the first spanning vector, which is a Cn plus 1. So the set that is missed by this chart is exactly a copy of Cpn. So that's what I'm saying. I mean, we discussed this earlier when I introduced the projective spaces, but I just wanted to remind you of this. Okay, so what do we do? So I just put I can write it like this. This is the complement of Cpn, and I have to remove a smaller set of u. So what do I remove? I take out all those lines in order to, I could just, in principle, you would just want to take the complement of u. So that would mean you would take out all those lines where z is greater or equal to 2, but that would not be an open set. And for this reason, I have to relax this to get I have to remove a closed set to get an open set. All right. And so what is this? Let me write it down again. So this is the set of all those lines for which z is larger than 1, but also those which are not contained in this chart. So this would be the set of all lines of the form 0, z, where z is non-zero. And this thing, that's a copy of Cpn. So that's what I was just saying. Good. So that is my set u and v. Now what is the intersection of the two? The intersection of the two is, of course, the set of those lines 1, z, where z lies in norm between 1 and 2. Right. Good. And I claim that we know the cohomologies of u, v, and also its intersection. Why? So first of all, u. That's the set u. The set u, so this is, diffeomorphic. So what is it? So that's under this chart map here. So that's completely contained in this chart map. And then under this chart map, it corresponds to those vectors which have length norm at most 2. So it's a ball, an open ball. So that's an open ball. And an open ball is homotopy equivalent to a point. Right, so it can be retracted onto a point. And remember, homology is invariant under homotopies. This is a consequence of this homotopy formula for differential forms that we proved earlier. So when I replace this space by something which is homotopy equivalent, they have the same homology. So u has a very simple homology, namely that of a point. Now u intersect v, what is that? This is also contained entirely in this chart domain. It's given here, and it corresponds to all those points whose norm is bounded from below and from above. So it's a big ball minus a smaller ball. And to what is this homotopy equivalent? To which simple space? Big ball minus small ball. It's a sphere, exactly. Which sphere? What's the dimension? 2n plus 1, it's a unit sphere in here, right? So which is r 2n plus 2, so it's 2n plus 1. Exactly, so that's, and we also know the cohomology of the sphere, so that's also very simple. And finally, what can we say about v? Maybe that's the most complicated part of the thing. So I have Cpn plus 1, and basically I have removed the ball from it, a closed ball. I have removed a closed ball from it. And then I'm left with this exterior of this closed ball, and then another copy of CPN. And in fact, I'm claiming that this V retracts onto this copy of CPN. So that would tell us that V is homotopy equivalent to CPN. And how does this retraction look like? Well, it's actually quite simple. How can you retract this? You just map, so the points which are already lie in this copy of CPN are mapped to themselves, and the points that lie in this, so this is a neighborhood of this copy of CPN, what I have here, this V, and the points which are in this part, there are the lines actually, they are mapped to the lines where you replace 1 by 0. So that means when you have this outside of the ball, this exterior of the ball, and a line corresponding to a point is mapped to the line where you basically go to infinity by rescaling the vector spanning the line. Okay, so the retraction of V onto that one is given by the formula. I can explicitly give it to you by mapping L onto itself if L is already in this copy of CPN, so it's already in this part. If L looks like this, and it's mapped, and if L looks like that, it's mapped to the line 0, 1, Z. So that's the explicit formula. All right. And the good thing is, the point, we know its cohomology, the sphere, we know the cohomology, and this cohomology we know by induction assumption. And now let's apply the Mayer-Vittori sequence to this situation. Okay, so what we are interested, so let's look at the Mayer-Vittori sequence. So we have HK, just copy it here, and then we have HK of M here. This goes to HK of the intersection. And then we go back to HK of M. And now let's see. So what is M? M is in this case CPN plus 1, right? So that's our M here. That's what we want to compute. And now U is homotopy equivalent to a point. So this cohomology, this part is 0, at least if K is not 0. If K is larger or equal to 1. And in the case K equals 0 is not interesting to us anyway, because H0 of CPN is, we know that is one-dimensional because it's a connected network. So for K equals 0, this statement is so that's R times the span of the zeros power of these two dimensions, just the constant functions that generate this. So K equals 0, we understand that. Good, so this term does not contribute. Here we have HK of CPN. So here we have to somehow use the induction hypothesis. Here we have HK of S2n minus 1. And we also know that this is 0 unless K is 0 or K is equal to the dimension here. So let's also say K should for the moment not be 2n minus 1. Last one, yes, thanks. Good, then we have a 0 here, and maybe we need one step to the left, which would be HK of the same of U intersect V, which is HK minus 1, sorry, which is HK minus 1 of the sphere. And if K minus 1 is not the same as 2n minus 1, this is again 0, right? So this is 0. So we have in addition to assume that K is not equal to 2n. So these two cases will have to be considered separately. But except for these two cases, what do we see? We have 0 here. Here we have what we are looking for. Here we have hk of CPN, and here we have 0 again. So we have a sequence 0, the thing we want to commute, a thing we know, 0. If you have 0 here and 0 here in an exact sequence, then this error must be isomorphism. So therefore, hk of CPN plus 1 is isomorphic to hk of CPN. And that's good, because by induction assumption we know that the Betti numbers are 0, 1, 0, 1, 0, 1, etc. And we see that this is still true for CPN plus 1, at least unless k is too large. So for k less than 2n, everything's okay. So for these cases, that's good. All right. In fact, this argument shows more. It shows that this isomorphism is not just some isomorphism, but this particular isomorphism from the Mani sequence, the Mani-Vittori sequence, is in fact, if you look at the arrows, so this comes from the map of what is it? So this is the inclusion of U and V into the total space. So this does not contribute, so it comes from the inclusion of this space into that space. So the isomorphism is actually induced by the inclusion of this copy of CPN into CPN plus 1. It's a somewhat stronger statement. So this inclusion map, in fact, induces an isomorphism on cohomology for this case. Of course, for this case, this cannot no longer be true if the statement of the proposition is true, because the cohomology of CPN becomes 0 as if k is larger than 2n. However, for CPN plus 1, that's not true for one of the two cases. So let's see. So let's look at these two cases separately. So let's start with, let's say, k for k equal n plus 1. Actually, this should be plus 2, right? I had to consider the case that this is the case when k minus 1 equals 2n plus 1, so k equals 2n plus 2. Okay, so let's look at this case. So we are interested in h2n plus 1 of CPN plus 1. So the sequence goes to 0 plus, and now I have h2n plus 1 of CPN. But CPN has only dimension 2n. So if the degree is larger than the dimension of the manifold, that's 0. So we end up at 0 here. So let's see what we have in front. In front we have h1 less 2n of the sphere S2n plus 1. But the 2n cohomology of the 2n plus 1 sphere is also 0. So that's also 0. So we have 0 here, we have 0 there, and therefore this must be 0. But that's good, because the statement is that for odd case, we have to get 0. And so finally, we are left to consider k equals 2n plus 2. So that's the last case. Let's see what we have. Okay, so k is equal to 2n plus 2, so we map 2. Again, the case so this is 0 anyway, and we are in k is larger than the dimension here, so that's 0 again. And here we have h2n plus 1 of the sphere h2n plus 1. Actually, that's not 0. So we have to go one step further left. So if we go one step further left, then we are again here, then we have this does not contribute, and here we have H2n plus 1 of CPn. So that's what we get. But the odd, by induction assumption, this guy is 0. So what we see is that we have an isomorphism from this cohomology of this field to the cohomology of CPn. And this we know, this is isomorphic to R. Betty numbers of this sphere are 0, are 1 in degree 0 and in dimension. So that's what we have, but we have an isomorphism here because we have 0 here and 0 there. Therefore, this is also one-dimensional. This implies H2n plus 1 plus 2n plus 2 of CPn plus 1 is also isomorphic to R, as stated here. And that concludes the proof. Okay. Now we understand completely the cohomology of complex projective space. So we could rephrase the statement of the proposition. We could say, okay, the cohomology of CPn, and in fact the cohomology is not just a bunch of vector spaces, it's a ring, it's an algebra over the reals, because we have the cup product also, right? So we have this multiplicative structure too. And as a ring, or an algebra, the thing is isomorphic to what? Well, we have to take the polynomial ring in one variable, which I call A. And A corresponds to the cohomology class represented by the Fubini form. A corresponds to this cohomology class. It generates the cohomology and all its powers until we get to degree 2n, and then everything is 0. So if we take this polynomial ring, then we have to kill the n plus first power. So we have to take this ring modulo the ideal generated by the n plus first power of A. And the isomorphism is given by this relation. And it's convenient to keep this in mind because it's convenient to do computations in this polynomial ring. Okay. So like that. And so this shows that this tautological bundle, it's so somehow simple. Right after the trivial bundle, this is somehow the next bundle that comes to your mind. If I ask you to define a line bundle on projective space, that's what you would give me. And we see that this tautological bundle is not trivial at all. Tautological is different from trivial. Its Chern class is non-trivial, but not just that. This Chern class represents, so this is the same thing as the first Chern class of the tautological line bundle. And it actually generates the whole cohomology of CPn as an algebra. Good. And now our next aim will be to compute the Chern class of the tangent bundle of CPn. Well, CPn is a connected manifold. And for a connected manifold, H0 is one-dimensional. And the Durand cohomology is just, in general, the Durand cohomology, what's the Durand cohomology degree 0? You have to look at closed 0 forms, modulo nothing, because there are no -1 forms. And so being closed means that the differential vanishes are locally constant. And so this the dimension of this zeros cohomology is just the number of connected components. So that's why we don't have to worry about it. No, we know that it's connected because so we have this map from Cn plus 1 without the origin to Cpn sending the vector z to the line spanned by z, right? And this is a surjective map, continuous, by the definition of the topology here. And this is connected. And the image of a connected space under a continuous map is always connected. You could also restrict this map to the unit sphere here. And I will come back to this map in a moment. It's also connected. All right. So the next aim will be compute the Chern class of the tangent bundle of CPN. Where really I want to consider this as a complex n-dimensional bundle, right? So that's a complex n-dimensional bundle. And so how can we do that? And as a preparation, let me use an auxiliary bundle, which is defined as follows. Define bundle E on CPN by, now let me give you the fiber, EL. So recall, L was a one-dimensional subvector space of Cn plus 1. And for the tautological line bundle, I just took L itself as a fiber, and now I take the orthogonal complement in Cn plus 1. And where orthogonal complement means the complex orthogonal complement. So, orthogonal complement with respect to the Hermitian scalar product and so on. So that means that's really a complex hyperplane, not just a real hyperplane, right? If I took the orthogonal complement with respect to the Euclidean scalar product on this space, considered as R2n plus 2, then I would get a real subvector space of dimension 2n plus 1, but I'm taking the the complex orthogonal complement, and so then this gives me an n-dimensional complex vector space. And okay, and now we have, of course, if we take the topological bundle, it's open, take the direct sum with this bundle, then I have the line sum with its orthogonal complement. So this always gives me, each line, this gives me all of Cn plus 1, obviously. And so this is independent of L, and therefore the sum of these two bundles gives me the trivial bundle of rank n plus 1. Let me denote this by epsilon n plus 1. So that should be the trivial vect n plus 1 C bundle on CPN plus 1 on CPN. So we have that, and this is already good enough to compute the Chern class of this bundle, and this will be needed for the computation of the tangent bundle. So let's compute the Chern class of E. So since these bundles are isomorphic, let's say, they have the same Chern class. So the Chern class of the tautological bundle plus E is the Chern class of the trivial bundle. And now we have this formula for the what happens when I take the Chern class for sums of bundles, namely the corresponding Cohomolgy class multiplier. So I have Chern of the tautological times, it's actually the cup product, C of E. And this one we know, C of E. And what do I have here? So this is this. So let me identify from now on in the notation simply. I switch between these two points. So when I write a little a, I mean actually this Chern class, right? So we have a here, C1 of the tautological bundle. But we also have the zero part of the Chern class. It's the total Chern class. And the zero one is the one. So we have that, right? And on the other hand, here, so what do we get? Just one, because it's trivial. So we get just one. And now in this ring, 1 plus a is invertible. So I can divide by this term. So I get 1 on 1 plus a. So what does that mean? Dividing by cohomology class of degree 2. What I'm doing the computation in this ring, and how do I compute this inverse? I expand it in the power series. In principle, it goes on, but since we kill off the n plus first term, it actually stops, and we end up with an, that's the last non-zero term in this power series expansion, and the correct sign is -1 to the nth power. So that's what we get. So I'm doing that just a computation in here. Right? So I could embed this into a power series in the variable a and work and always do the computation with this relation. So then this gives you that. So we have this bundle, the Chern class of this bundle. Good. And now how does this relate to the tangent bundle, which we are really interested in? And this is given by the following lemma. Namely, the tangent bundle of CPN is isomorphic to the bundle obtained by homomorphisms from the tautological line bundle to this new bundle E. So the fiber at each point L consists of complex linear isomorphisms from tau L to EL. Let's do a dimension check, if this is possible at all. This is for over each point. This is one-dimensional complex vector space. That's an n-dimensional complex vector space. Remember, this was this orthogonal complement, so that's n-dimensional. So the space of homomorphisms has dimension 1 times n, which is n. And that's also the dimension of the tangent space of CPN as a complex vector space. So it can be true, right? At least. So dimensions match. And now I have to explain how this isomorphism looks like. All right, so how does this isomorphism look like? And we use the Hopf vibration for that. And I had it on the board already. I call it H from S to n minus 1 to CPN. And it's simply the map that takes a unit vector Z in Cn. This is the unit sphere in Cn. Takes the vector and maps it to the line spanned by this vector. So that's the Hopf vibration, the Hopf map. And okay, so that's then in here. And now this Hopf map is really a submersion. Let me call it Hopf map because I can explain the Chern vibration. And now H is a submersion. So it's smooth and it has a surjective differential. So this is 2n-dimensional if you consider it as a real manifold. This is, sorry, there's something wrong. It's a plus, because this is sitting in Cn plus 1. Sorry. So that has one dimension more than that one. So that's what I want to say. Alright, so that's a submersion. And if we look at its differential at some point z, so this goes from the tangent space of S2n plus 1 at z onto the tangent space of Cpn at the corresponding image point, which is the line span by z. And now let's see. So this tangent space of a sphere, we know this very well. So the tangent space of a sphere can be naturally identified with the orthogonal complement of the base point. But we have to take the real orthogonal complement. And the real orthogonal complement of the base point splits into the complex orthogonal complement, and then one dimension is missing. So the complex orthogonal complement is n-dimensional, complex n-dimensional. The real orthogonal complement is real 2n plus 1 dimensional. So there's one dimension missing. So what is it? So it's the real span of I times z. Because this is indeed, it's real orthogonal to z, but not complex orthogonal to z. Right? So that's exactly the direction that we were missing. Good, so we have this splitting of the tangent space of these odd-dimensional spheres. We have this canonical splitting. And now, my claim is that, in fact, this part here is exactly the kernel of the differential of the Hopf map. And why is this? Well, this is because whenever, so because for, let's say, an alpha in C with norm 1, what we can do is we can look at the left multiplication by alpha. So we can, if I can take a unit vector here, multiply it with alpha, then I get another unit vector. Look at L alpha from the sphere to itself, just by mapping z to alpha times z. And now, if we have this map, L alpha S to n, and then we have the Hopf map going to Cpn, and similarly here too, and this commutes. And why? Well, that's very simple, because z and alpha z span the same line, simply. Right, so and here this just maps to the line span. So that's obviously commutes. And now, if I take this tangent vector, or the corresponding tangent vector here, which corresponds to I times z, then this can be represented by the curve. So I times z is the differential dt equals 0 of the curve of what curve? It's of a curve of such alphas, namely of the curve e to the I. E to the I t times z. Right? If you insert t equals 0, you get your point z. If you differentiate the thing and then put e equal to 0, then you get an additional factor of z. So in other words, this vector here can be represented by a curve consisting of those alphas, so such that the corresponding image curve in Cpn is 0, is constant. And so if you differentiate the image curve in CPN, you get 0. So this is why these things certainly lie in the kernel of this differential. And it's a submersion, so the thing must be still, so the differential must be surjective, so therefore restricted to the orthogonal complement. It must be an isomorphism. So dh of z from z perp onto the tangent space of CPN, the corresponding line. So that's an isomorphism. Because these have the same dimension. So this is the n-dimensional complex and this is the n-dimensional complex. So this is how the situation looks. And good, so that's the general reminder of the Hopf map. And now I can give you the isomorphism that is stated in the lemma. Because the Hopf map allows, so this sets up the link to tangent space of CPN. Right? So for L in CPN, define isomorphism chi L. So that should be an isomorphism from this one, homomorphisms from tau L CPN to EL, from this homomorphism space to the tangent space of CPN at L. So I want to come up with such an isomorphism, right? I want to do that here. And for this it's useful to remember what this is. I mean, this one is just L, right? So this is homomorphisms from L, and this one is L perp. So homomorphism, so I'm looking at homomorphisms from L to L perp, and I'm claiming that to each homomorphism I can associate a tangent vector in an isomorphism way. How to do this? By. So first I choose a representing element here by choosing Z, something which generates L, and I want to do this such that it has length 1. So I take a unit vector that generates the line, and then I set phi L of such an homomorphism U to be what? Well, Z is an element of L, so it's an element in here, and U is a homomorphism from here to there, so I can apply U to Z. What I then get is an element in here, in L perp. And this L perp is exactly this space here. And so I apply the differential of the Hopf map to it. And then I end up with a tangent vector in CPN. And I'm claiming that this is the required isomorphism. So first, of course, we have to check that the thing is well defined, because I've made a choice here. So chi L is well defined. And so we have to see what happens if we make another choice for Z. So let Z and Z prime be two elements in L intersect sphere, unit sphere. And if that's the case, so these are two vectors spanning the same line, so they're collinear. And since they are both in the unit sphere, the factor must be of unit length. So I can write Z prime as alpha times Z, where alpha has unit length, right? And then I have to see what happens if I replace Z by Z prime in this formula. Okay, and for this I need the properties of the Hopf map. Alright, so let's do let's see what happens if I insert Z prime here. Well, this is pH at Z prime, and now this is U of alpha Z, but U is complex linear. It was an element of this space. It's a complex linear map, so I can drag the alpha out here. Which means I have just applied my left multiplication to U of Z. Now this left multiplication is a linear map, so it coincides with its own differential under this identification, so I could write this as dHz prime composed with dl alpha at Z applied to U of Z. By the chain rule, that's the same thing as H of Z composed with L alpha at Z applied to U of Z. And by the commutativity of this diagram, that's the same thing as H. So that's dH of Z applied to U of Z. And so we have the same expression with Z prime and Z. So that shows level fineness. So that's really this commutativity of this diagram, which is behind that. And okay, that's good. And the next, so it's well defined. It's also injective. Why that? Well, let's see. Suppose we have chi L of U being 0, so meaning that dH of Z applied to U of Z 0. Now remember, this term is an element of L perp, so which is Z perp in this case. And when restricted to Z perp, the differential of the Hopf map is an isomorphism, so it's injective. So that means if this is 0, then that y must be 0. So that's an element in L perp. But now remember, U is a homomorphism from a one-dimensional space to L perp. And we have inserted a generator of this one-dimensional space here. So a generator, so this linear map from L to L perp, when applied to a basis, so just one basis vector of L gives you 0, that means that the linear map must itself be 0. So this implies that U is equal to 0. And that's injectivity, right? So chi L applied to U is 0 implies that U itself is 0. Okay, and now by dimensional reasons, since Z perp and the tangent space, let's see, since this space is n-dimensional and that space is also n-dimensional and the linear map is injective, it's an isomorphism. So dimensional reasons. Imply that chi L is an isomorphism. And that's what we wanted to have. So we have set up this isomorphism between the bundle we are interested in, namely the tangent bundle, and two bundles we pretty much understand already. Now we can use this to conclude the computation of the Chern class of the tangent bundle. Alright, so let's see, how can we use this now? Alright. So using this lemma, we have, I did not prove smoothness in L. In order to do that, yeah, you could do it in charts. I didn't want to mess with that. But since it's a natural construction, it will turn out smooth anyway. I made no choices except this one choice, which turned out to be irrelevant. Yeah, it's true. In principle, I would have to prove that this is actually also smooth in L. So using the trivializations we have, but this one I also did not do this for the bundle E. In fact, I only showed it's a pre-bundle. I skipped the smoothness, so that's true. All right, so let me compute the Chern class. In order to so let's see. So here we have the tautological bundle, and here we have this bundle E, and the homomorphisms between the two, which, by the way, I could also write as the dual bundle of this one tensor that one. That would be the same thing. And okay, and so I know that this is isomorphic to the tangent bundle of CPN. And now let me add something here, namely I add a trivial line bundle to that. I have to do this here too, of course. And now I can rewrite this as homomorphisms tau CPN E, and the trivial line bundle I rewrite as homomorphisms from tau to itself. If you have any line bundle and you look at the homomorphism bundles from the line bundle to itself, you always get the one-dimensional bundle, right? Homomorphism is 1 times 1 dimension, is 1 times 1 is 1. You get a one-dimensional bundle, but it's also trivial. Why? So why is this bundle trivial? It's not just for this, has nothing to do with the tautological bundle. This holds for every line bundle. If you take a line bundle, you take the homomorphisms from line bundle to itself, that's a trivial line bundle. Why? One way to show that a bundle is trivial is that you have global frames, right? So the global section, in this case it's one-dimensional only, so you would need a global section of this homomorphism bundle which does not vanish anywhere. The identity. So to each L you associate the corresponding identity. Right? Now it's pretty clear, it's obvious. Why didn't I think of it? Yes, exactly, it's the identity. So that's why this bundle is certainly trivial. So I'm rewriting it this way. Now I want to combine these two things. They have the same domain. This lands in one space, this lands in another space. So certainly there's, if I have a homomorphism from one space here and from the same space there, that's the same thing as having a homomorphism to the sum of the two spaces. Okay, so that's, I could also write like this. But this bundle we know. What is it? What is this bundle? Right, this is the fiber here is L and here L perp. So this gives me the trivial bundle of rank n plus 1, which at the same time I could write as the sum of epsilon 1, epsilon 1, epsilon 1, etc. Do that. N plus 1 times. And now I can undo this thing and take the things apart again. So that would be the same thing as homomorphisms from tau logical bundle to epsilon 1. And the whole thing n plus 1 times. Now this bundle here that occurs n plus 1 times has a name. What is it? So for any line bundle here. It's a dual bundle, exactly. So I can write this as tau CPN star added up n plus 1 times. And that's good because now we have a formula here we have the dual bundle of the tautological bundle. We know how to compute we know the Chern class of the tautological bundle. We know how to compute the Chern class of a dual bundle. And here the only thing that we have is a trivial bundle, which does not change anything. So from this we can read off the Chern class. Let's do it. So what do we get from this? If I take the Chern class, so here I have a Chern class of T CPN plus epsilon 1, which is the same as the Chern class of this sum, n plus 1 copies. Now, by the product formula for the Chern class, that's the same as Chern class of CPN times Chern class of epsilon 1. But that Chern class is trivial because it's a trivial bundle. So here we get the Chern class of the tangent bundle that we are looking for. And here we can use this product formula for the Chern class n times, and then we get the Chern class of the dual bundle multiplied n plus 1 times. Now this Chern class we know, so this is 1 plus a. So the Chern class of the tautological bundle is 1 plus a. And what is the Chern class of the dual bundle then? How does the Chern class of the dual bundle relate to the original bundle? What do I have to do? So there's this alternating sign, no sign here, one sign here, and then there's nothing else left anyway. And we get this n plus 1 times, right? So that's what we have. But we have computed it. And so let me raise the result. So we have shown that the Chern class of the tangent bundle of CPN is given by this formula. So I'm again doing the computation in the ring, which I have probably now erased. And I identified the cohomology ring of CPN with this polynomial ring. Now this can be expressed in terms of by the binomial formula. So what would be the binomial formula? Well, this is the binomial factor n plus 1 on k, choose k, and then I have to apply this to the powers of minus a to the k. So that's the binomial formula. But in fact, remember we are on CPN, and the n plus first power of a is actually 0. And that would be the last summand here, right? So where k is equal to n plus 1. That's actually 0, so I should only sum up to n. So that's the formula. And if you start expanding it, well, k equals 0 gives 1. And then n plus 1 on 1, what is it? That's n plus 1 factorial divided by n factorial times 1 factorial, which is n plus 1, right? And then we have this minus sign, so we get minus n plus 1 times a plus higher terms. So already this lowest term, this is giving me the first Chern class. This is already non-zero. So therefore C1 of TCPN, which is minus n plus 1 times a, is non-zero, and therefore we know that the tangent bundle is always of CPN is always non-trivial as a complex vector bundle. For spheres, the corresponding statement would not be true. The tangent bundle of spheres is sometimes trivial, sometimes it's not trivial. In most cases, it's not trivial. But for CPN, for projective space, it's always not trivial. And now, in fact, there's an interesting special case to that. Namely, example, n equal 1. Because what is CP1? After all, what is it? It's a two-sphere. Yes. It's a two-sphere. And so this shows that the tangent bundle of the two-sphere, considered as a complex line bundle, is non-trivial. Okay. Now, so that's what we see. T tangent is non-trivial as a vector 1C bundle. And what does this tell us? Well, this tells us that certainly, so that's a rank 1 bundle, so there cannot be a global section which is nowhere vanishing. Right? So, because that would mean we have global frame, don't have that. So, no global smooth section. And the section of this is just a vector field, right? Nowhere vanishing. So in other words, we have shown on the two-sphere there are nowhere vanishing global vector fields, so we have proved the Harry-Wald theorem. For S2 along the way. And I guess that's a good time to stop. Thank you very much.